welcome to Best Buy. My name's Joel Crabb. I'm the chief architect for BestBuy.com. I hope you enjoyed your day here. For us, I think it's felt like another day at work, so it's always fun. Today, my colleague Kanan Swaminathan and I are talking about how BestBuy.com has been using Cassandra and Riak to help serve up the replatforming efforts that have been ongoing for the last 2 or 3 years for BestBuy.com. And so it's more of it's not really a head-to-head kind of, which one's better than which, but they do both have their unique properties. And we'll try and get to the differences and why we picked 2 different systems and how potentially, you can use them in your own work. So with that, I'll get started. What is going on? Yeah, I don't know why that happened. So for everyone from Best Buy here, this is the official Best Buy slide deck and the official Best Buy things you're supposed to have in your deck. If you saw any other Best Buy deck here that didn't have these things, they didn't talk to PR. But in any case, obviously Best Buy, everyone here knows Best Buy. The things I try and do when I give presentations, as I work for BestBuy.com, is I'd like to have an uptick in sales during the presentation. So I would ask everyone here, we do a lot of stuff, we sell a lot of things. Go to BestBuy.com, buy something, because then I can go back later and look at the logs and see what actually happened. So yeah, we're the world's largest multi-channel consumer electronics retailer, 10th largest online site, commerce site. 1.6 billion visitors a year, and we have one of the largest loyalty programs in commerce, in general, not just e-commerce. So the next slide is the next one. I'm just going to let people read this for a little bit. Best Buy, obviously, we think we do a really good job selling electronics and servicing them, and we'd like it if you stop by the store too. But BestBuy.com is a better place to buy stuff because that comes towards makes us look better, and not these people down here. So anyway, because I know you guys are going to ask me some nasty questions at the end, so I have to get my digs in first. All right, so let's get going. I introduced us already, so we can just jump to the next slide. OK, so VoiceHive is a kind of small startup that has been offered up as the way to ask questions during these presentations. Maybe you saw one earlier in the day. We're trying it out. If you want to ask a question, go there, log in, and type in your question. It's anonymous, so you can ask anything you want. At the end, we'll go take a look at what the questions were. Cassandra and Riak is the name you have to go click on to get to our thing. Or otherwise, just raise your hand, and I'll call on you, except for you. So NoSQL at BestBuy.com. What are we doing with NoSQL? The reasons we picked NoSQL databases is really for the schemaless design aspects. We have key value systems, the sparse column systems. Riak is key value, Cassandra is a sparse column, and the non-relational data. The other very large reason we pick these is for the distributed nature of the systems. These are data systems that are built to be distributed from the start. And that's a big thing for us. And the big data part of this, is I often get asked about, isn't such a big thing for BestBuy.com. We have a lot of data, but we're not using the systems for the big data parts of their capabilities, but we are using them basically for schemaless and distributed nature. So if you haven't been to BestBuy.com, this is what it looks like. I'm hoping this isn't a surprise to everyone. But first, before we really get into the 2 databases, it always pays to get a little bit of context. And BestBuy.com is actually the 4th highest traffic in e-commerce last holiday. So it's Amazon, Walmart, eBay, and then Best Buy. So we get some of the highest traffic that any commerce retailer in the United States and North America sees. So that drives a lot of how we do software development and architecture, because we are planning for massive spikes. 7 times normal traffic. It's really actually closer to 10 times, because this graph here, which is from
2013.
Yeah, it's from last year, 2013 holiday. It's 7-day moving average, so that peak of about 7 times is really slightly smeared over 7 days. So actually, it's even higher than that. It gets about 10 times their normal peak. If any of you run systems that are already very large to start with and then get 10 times larger at times of the year, you can understand the kind of problems that we face when we're trying to scale BestBuy.com. As a comparison, you can go forward one more. Walmart's traffic follows a very similar nature. The big spike, if you don't know, is around Thanksgiving, Black Friday, Cyber Monday. And one of the nice things that we saw this year is we actually caught up a lot in terms of traffic to some of our rivals. So we're all very proud of that. Next slide. The other thing that we're always trying to do, and so one of the main reasons we've been replatforming BestBuy.com for the last couple of years is just to get more flexibility in how fast we can build this system. So this looks very simple. If you go one more, that low price guarantee we put in, this is actually last year. That would have taken us like 2 months was the estimate to do it in the old architecture. And obviously that seems kind of crazy. But in the new architecture, it's a half a day, about a day of work. But that's kind of where we were at about 3 years ago, when something that seems like a very simple change was extremely difficult just because of the scale and the size and the way that the systems were written. So the other thing that we have is very, very high reliability goals. If Best Buy goes down for even 10 minutes, 15 minutes, half an hour, it's pretty much on the wire immediately, and people are calling us about, hey, did you know that BestBuy.com is down? Usually we know that already, but when we don't know, it's really a bad thing. So we're basically asked for 100% availability. Obviously, that's not possible, but we are actually striving to build systems that have built-in disaster recovery, implied high availability, so that we really can get to the point where we are basically 100% available. And in general, the bar for .com systems is about a 2-second response time. When you click on BestBuy.com, you want to see something in less than 2 seconds. If you get beyond 2 seconds, that's when people start leaving. And we did this last year. We achieved pretty much 100% uptime in our cloud architecture over the last holiday. So a couple just quick things on clouds. As we found, as we've been working in clouds now for the last 3 years, is the clouds, they do fail. You'll see them on, Amazon's cloud has failed, Rackspace's cloud has failed. And when those things happen, you basically have to be planning for the fact that they will happen and design your systems accordingly. So our system is built to span multiple clouds, multiple regions, and even multiple vendors, and even have Best Buy be part of the system as well. So if one of these things goes down, we can swap over to the other system pretty much instantly or all the time. We just drive traffic to different sides of it. And this gets us to what we're trying to get to at that 100% availability. The other thing that fails is the cloud is out in one of your vendors' ecosystems, and all of your data is within your data center, or for our terms, our BestBuy.com data center. The connections between the cloud and the data center fail actually frequently, more frequently than we would like. But you have to build your systems, especially the cloud-based systems, such that they're built to absorb a failure in that connection. And so what we have in our cloud is basically everything is cached so that even if it fails very intermittently. From the user standpoint, they don't actually see any difference. The text, the data might be a little bit old, but we're talking about seconds and minutes and not hours and days, so no one ever notices. Next slide. And at a really high level, this is kind of what it looks like as a picture. We have a CDN, a content delivery network that sits over the top of everything. We have multiple instances of our cloud stack. And then at the bottom of it is our Best Buy data center, where all the transactions occur. It's very safe. It's all in the data center. No transactions occur in the cloud, so go ahead and keep buying stuff. And so now I'll jump into the two systems that we use. So Riak is a key value style NoSQL database. Does people here, I should have asked earlier, do they know what NoSQL databases are, or should I explain? Does everyone know? All right, enough people know. You can ask your partners that don't know later. But anytime you're designing a system, especially for a large company like Best Buy, you really need to start with what's the business need, what's the business requirements. For us, it was easily add new attributes to products. So we sell lots of products. There's something 650,000 right now on bestbuy.com. And these products are in many, many categories, and they all have different attributes attached to them. They're constantly adding new attributes. So one main part of the system is the ability to add new attributes pretty much anytime you want to and very easily. We wanted to reuse all the content system feeds that we already had. It's a very large system already, and we didn't want to actually rewrite these things. And we wanted to be able to provide this data to all of Best Buy, so put it out there as RESTful services and let people use it. From the technical side, go back one real quick, sorry. We wanted to scale to Best Buy's needs. We saw our scaling patterns in the graphs earlier. We only replicate out to clouds. We don't actually let the clouds call back to us. And I think the last one is pretty much the same thing. We call it the product catalog API. We have about 30 users just within Best Buy itself that use this system for their product data. So slightly lower level picture of what the cloud architecture of Best Buy looks like. We have multiple installations or regions and availability zones. And then we have the back-end data center. And what we're actually talking about today is the next click, is the product data. So that's what Riak does for us. It's the product catalog, product data system. And so to give a couple quick examples on the next slides, this is what our product detail pages look like. If you click the next one, all this data is coming out of our product catalog. So if we go kind of quickly through the next two slides, you can see all this is the data that you see on the site. Pretty much everything you see in a product detail page at bestbuy.com comes from Riak. So click the next one. I think I maybe have one too many of these, so keep going. OK. So why Riak versus any other NoSQL data store? One of the things for us is a key value data store, which means that you can pretty much dump anything you want into the system. And Riak is basically structured to put it in there and then be able to search on it or quickly change things and add values. The other part of it is we can have the different attribute sets for the different types of products that we have. So if you have appliances, they have different needs. If you have TVs, they have different needs. If you have blanking on some of the other stuff we sell, mobile phones, et cetera, then they all have different sets of attributes. And so the great thing about a key value store is I can just put all these in the same bucket, and it doesn't really matter because it's just kind of unstructured data at this point. It has hub and spoke replication, which is a big thing for us, because if you saw the pictures from before, what we do is we replicate from our data center to all of our clouds. And it's a single direction. We only replicate out to the clouds. And so for us, having the main data set within bestbuy.com, we can replicate out to as many clouds as we want to. And it gives us a very nice model of being able to push the replication of all this data out to where we actually serve it up to the customer. The other thing with Riak is very nice architecture for resilience. It's been proven over the last few years that we've actually had no failures. It's never been down in 3 years. And we've actually had instances fail. The first time we deployed it on new hardware. It was a 5-node cluster. And put it on in production. Everything was operating. Came back 3 days later and noticed that one of the nodes had actually gone down about an hour after it was installed. It was new hardware, but we never noticed because we didn't have our monitoring that well yet. That's not the best thing in the world, but the best part about it is it kept working and no one even, we couldn't even tell. So it's got a very resilient architecture, which is nice for us. Now, next slide. The other thing that it did for us is it allowed us to kind of contain our legacy side of bestbuy.com for a much longer time than if we had tried to replace the whole system. Riak has allowed us to basically bridge kind of our old and new systems. The data and all the product data comes in, and it comes into the new cloud system, and none of those others, they all are constantly morphing and changing, but they didn't actually have to be rewritten to use any of this. We can then expose the same set of data to lots of different places in Best Buy. Like I said, there's about 30 different groups within Best Buy that actually use the product catalog. And it actually has put us to the point where we've been able to extend the decision on how to start to retire some of our legacy on the .com side. So a couple other quick architecture pictures in terms of resiliency. So you can see what we have is we have multiple rings, a ring in every cloud and a ring in the data center. And on the next click, you can see that you can lose any of these types of connections at any time. And this does actually happen to us as we're operating. The architecture that Riak allows us to build makes it so that we can lose any of these things, and it doesn't actually matter. We're still serving up the pages. They might be a little bit delayed in terms of the content, but like I said, in general, no one ever notices because it's fairly fast. And then this is just basically a basic data flow diagram that shows how all the data ends up flowing out to the web application. Could probably gloss over this one. Basically, the point on this slide was to show that we're doing extraction from the legacy system, pulling that data into the cloud systems, and then replicating it out to the clouds. So when we get down to some of the lessons that we've learned as we've actually operated the system for the last 3 years. Go.
Curious about your legacy systems and importing data, like getting data in initially. Are you using classic SQL databases and then doing transforms on them to push those out to NoSQL? And do you do management in those, or are you NoSQL all the way through now?
You pretty much nailed it on the first one. There's classic, I like that term, classic relational databases. Yeah, it's a classic relational database. We basically have something that sits over it, extracts. It has listeners on it that can tell when the data in the database has changed, and then we pull it out and push it into the Riak. It takes about 5 minutes for that kind of cycle to happen. So if something new gets in our database, it takes about 5 minutes to get out to our cloud regions and then be served to clients. So one of the things that we learned over the course of using Riak was that the search was a killer in terms of our application performance. And so at a certain point, we decided we just had to take this out. So some of the graphs that we saw when we took this out really made us realize that, hey, that was a great decision. Because if you can actually see on the left side for you all, our usage of the processors was very variable, and basically is when the search came in, it spiked the processor up, and then when it went away, everything was fine again. As we took the endpoints out, now we got a nice graph. I think that's I think there's 8 nodes in that graph right now, and that's just one of the things that we learned. If you know your Riak pre-Yokozuna is their new search that they've just put out in their newer releases. This was before Yokozuna. We're on a slightly older version. So if you're going with the new stuff, we haven't actually gone to that yet. The other things that we learned is that multi-data center replication is extremely hard. We're pushing large amounts of data out all these pipes from our data center to multiple clouds pretty much constantly. What we see here is we're pushing about 4,000 objects a second. And this is just to a single cloud region. And it took about 1.5 hours, and this was only a partial update of the system. So when we do full updates, it sometimes takes 8, 10, 12 hours just to push all the data out to the systems. But replication, while it used to have this feature where it would fail silently, which is not a good thing. And so we ended up having to write a few listeners or watchers on the system to see that every once in a while run them and see what hasn't been updated lately. That's actually now been fixed in our newer versions, but at the time, it was one of the problems that Riak had. And we actually have been working very closely with the Basho team to fix a lot of the problems that we've had over the years, search being one of them. And the other question that we often get is, well, would you do this again, or did it succeed? And this is, I think, a great slide to show how we think it's actually working very, very well. So a general request for us takes about 4 milliseconds, and that's at the 95th percentile. So I would hope everyone here considers that fast. 4 milliseconds is pretty fast. And even when we picked this graph because what we had was a single zone failed, and so the other zones started to take that load. So you see the two, if you can see them, the pink and the red line are straight in that one side because they're not taking any load now. The other zone spikes up because it's all of a sudden taking a lot more load. But as we can see, even at a lot more load, it's still 8 to 10 milliseconds and not 4. It's still very, very fast. And that was the course of about an hour where that other zone was down. And when it comes back, it's basically just back online and no one even notices. So for us, we've had failures. And we've been able to scale this to extremely high levels. And what this is that 4 millisecond time frame is the same pretty much no matter what load we have. So over Thanksgiving this last year, this graph's barely budged. At our highest peak loads, pretty much serving out at 4 milliseconds all the time. So almost complete horizontal scalability, which is oftentimes what we're going for in these large enterprise systems. So with that, we'll switch over to Cassandra, which is the other NoSQL system that we use.
All right. Can you hear me? Yeah. Excellent. So if you flip the page to Riak and you decide to use Riak, I would just watch out and hold you for probably another 15 minutes to talk about Cassandra. And then I think we'll open up the floor to where you can actually dissect both Riak and Cassandra from the standpoint of what's supported in each. Why did we pick Riak? Why did we pick Cassandra? And what would you actually do going forward when you have to pick a solution to cater to the needs of your problems? Moving on. The problem that we were going to solve with the Cassandra solution, and there are a couple of Cassandra solutions here at Best Buy, and I'm going to talk primarily about the customer graph solution in the course of this presentation. The context being that when we were asked to look at a customer data set in our enterprise, we had more than one web property, we had more than one identity provider. So the task really was to set up a platform that can essentially be a single identity provider for the enterprise over time. The second reason was building an adaptive model to support a 360-degree view of the customer. So historically, we haven't been great at recognizing the customer across channels. And we have been relying a lot more on inference than deterministic schemes to actually identify the customer. So part of what we were trying to solve for was essentially establish an extensible framework that will allow us to deterministically identify people irrespective of which channel they are on. The third piece more was essentially giving ourselves the flexibility to integrate with external identity providers. If there was a need to identify the customer on bestbuy.com and say potentially link their persona that they have on, say, another social site as an example, you needed a framework that will easily allow you to do that and essentially encapsulate the data sets that are at all these federated stores for you to be able to drive some recommendations. That's more or less on the business side. The technical side, again, I think you have seen the numbers that Joel had put up earlier on the kind of access patterns and the requests per second that we want to be able to support. The second aspect is there is this notion of a risk-based authentication that we need to be supporting. So as an example, if you are an identity provider, part of your role is to also ensure that the data that is stored is actually secured. So if you actually see authentication attempts come up, you end up looking at whether that was really initiated by, say, a bot, because you actually would have heard about all the compromised accounts at all the other locations. And so when you actually have fraudsters mining data from other sites and essentially trying to compare the data sets that have been compromised on other sites with our site, you are really looking at putting a risk-based authentication support in place to thwart those attempts. And part of the challenge was this solution had to essentially help with that. At a high level, you should start seeing the differences between the Riak-based architecture and the Cassandra-based architecture effective from here. Joel referred to the fact that there were multiple rings, with each data center having its own ring in the React model. The flip side here is there is one ring, and it's essentially distributed across each of these data centers on the edge. So the other aspect about this API, again, is the distributed nature. And in the use case where we were talking about the product catalog, the writes would actually happen in the data center, where the reads would actually happen at the edge. This solution, on the other hand, essentially allows you to write anywhere and everywhere. If you take away the customer usernames and the passwords out of this mix, you should be technically able to write any updates to the customer entity at any point on the edge. So that's really where the differences start to show up, because this is in support of distributed writes, whereas React would have actually given you the notion of a master read, then a slave read on the edge. Moving on. Essentially, the concept is more or less, it would come out from the name, where we say we want to be able to support a holistic view of all the actions that the customer takes on the site, essentially capture all the preferences that the customer initiates and provides us. Think of it as a taste graph and not necessarily as a clickstream data capture solution. Again, this is going to result in more deterministic ways of actually identifying the affinity associated with the customer in terms of their tastes and preferences. And so what we are really having out here is a framework where when you actually set up the customer metadata, you can necessarily record the devices that they currently use. If you go to bestbuy.com and look up our wish list feature on the site, you would actually find that a customer has so many lists, and then when you have to walk up the relationship tree to see, is a given product on any of these customers' lists? Or is this device being used by any other customers? So you actually have this bidirectional notion of how you walk up and down these relationship trees. And that's really the power of this Cassandra data model. Theoretically, you would actually think of a columnar structure as, hey, we have a row and we have columns. And now you have a property of Cassandra where you can actually index each column, and you can technically have up to 2 billion columns in a row. I don't know if you will ever need 2 billion columns on a single row, but that feature still gives you the flexibility to where you can start indexing the attributes that you associate with each entity. And so unlike a key value construct, where when you have a product with one or more attributes and you are in the need of looking at a variety of attributes driving your search patterns, here you are where you basically end up essentially denormalizing your data structures in such a way that irrespective of the pattern that you put in place, you're not really relying on secondary indices. And so that's really where this lends itself to a REST-based API infrastructure, which essentially is adaptive. So part of the challenge here is, by virtue of this solution being so adaptive, when a new request or when a new initiative is spun up, the obvious question is, okay, I want to be able to capture, say, a customer's shopping cart and a list of items that the customer added to the shopping cart. Is there an API available? So the answer is yes. Now then you get into the discussion, then you start really dealing with how do you actually query upon the data set. The whole data model is predicated on the ability to query and the ability for you to essentially walk up the tree, a typical graph. So you can actually look at varying dimensions to how a customer has been, say, acting upon a shopping cart or acting upon the offers that we actually provide. So it's all predicated on how you query and how you can actually drive your analytics use cases. So think of a pattern where eventually if you were to have a clickstream data capture solution and a user taste graph solution, and if you were to ingest both these data sources, it can get very powerful in terms of identifying the customer behaviors and actions that they do on the site. You can actually do segmentation too with this data set. So the key here is to actually add more and more data sets to this platform for you to be able to then get to a state where you can drive all these recommendations. One last thing, sorry. You would actually see the use of a predicate or a verb when we talk about an association between entity A and entity B. And Again, it's modeled in such a way that any entity can be associated to any entity with any number of verbs. And again, if you wanted to ever find out who are all the users who have marked, say, our Richfield, Minnesota store as a preference, the answer is right there. Who are all the people who have used Samsung Galaxy S3? The answer is right there. So the notion is it's not a subject, predicate, object construct. It's more if you're familiar with predicate calculus or if you're familiar with the notion of a predicate being modeled independent of the subject and the object, this is the pattern that has been used. Go ahead. Why Cassandra? Again, both of these NoSQL stores, Riak or for that matter, Cassandra, form the Dynamo white paper. And so they have just adopted different patterns in terms of how they actually distribute the data sets across all these data centers. But from a Cassandra perspective, there is no single point of failure. The writes are really fast with Cassandra because there is nothing called a master primary. There is nothing called a master slave replication. It's a peer-to-peer architecture. And that's probably one of the salient features here where the writes are just amazingly fast. It delivers an atomicity, isolation, and durability. And again, whenever you talk about distributed platforms, eventual consistency is the underlying theme. It's no longer ACID. It's no longer waiting for a lock to be released on a database table for you to be able to update. It's all predicated on the eventual consistency paradigm. Tunable consistency for reads versus writes. So for example, when I keep talking about distributed writes as an example, let's say I get a write on a customer entity at one of the edge nodes. There are options. I can wait for all the replicas across all the data centers to respond back to the write, or I can do a local quorum write and let Cassandra do its job of replicating it to the other data centers. Similarly, on a read, I can pick whether I want to be able to do a local quorum or either I just want to read from the nearest replica. So there is tunable consistency depending on the use case that we need to be implementing. And the other aspect is the data sets have an expiration to it. So if you ever wanted to implement, say, clickstream data capture as a use case, you don't really want to be holding on to that clickstream data set forever. So you want to be able to set a time to live or an expiration on that data set so that you can not necessarily trigger an out-of-band event to actually purge. There is no more of this bad job running at periodic intervals to purge the data set. You write it with a TTL, and should there be no events or writes to that entity, the data just gets automatically out of the ecosystem. I think those are some of the key reasons why we pick Cassandra, and these are some of the features that we actually continually use and leverage for a variety of use cases. This is a little bit more detailed in terms of what we have learned from a data modeling perspective. So when you actually transition from a relational database role to a NoSQL platform, you'll have to forget about transactions, distributed XA transactions. You have to start thinking about REST. You have to start thinking about how would you query that data. Typically in a relational store, you always get into this crazy situation. Am I doing optimistic locking or am I doing pessimistic locking? I'm doing no locking here. There is no lock, and there is no get, and then a write. I'm not waiting for cycles to just wait to do a read, get the view of the record that exists at that point in time, and then do a write. It's a write. It's idempotent, and you essentially hit columns. So when I talked about a row and you have the ability to do 2 billion columns in a given row, you're not ever going to be able to read the row, look at the row, dissect the row, then figure out which column to update. You're just updating the column right then and there. And then when you actually read, the last write wins. And that's a property that's available with Cassandra. I mean, Riak does have the ability to do vector clock schemes, but that's more prevalent for use case in a B2B setup than a B2C setup. End of the day, even with vector clock resolutions, you always have this notion of you have to be able to resolve should there be any siblings. And eventually, the paradigm is the last write wins. So Cassandra natively supports last write wins. The other piece, and for people who have come in from the RDBMS construct here, you would actually have the notion of, you would create a secondary index on a column in a table. Nobody pays attention to whether it's actually efficient. And think of a column with all these attributes that you want to index. So let's say as a user, you want to be able to query them by their first name, last name. You want to find out all the people who are, say, loyalty members and whoever. You would actually end up creating as many indices as you need. Now, if you put an API platform in place which basically can index any attribute on any entity and set the stage up where you can actually query at no cost for having to create those indices, you don't have to worry about whether the index is still current or not. It's not an index on values. There is this support in Cassandra for actually being able to do an index on values, but then it doesn't scale. And that's one of the reasons why Oracle doesn't scale either. So anytime that we have been looking at it, we have always been modeling a secondary index as another column family, a denormalized data structure, and then you take the hit in terms of ensuring that anytime a property on an entity is updated, you end up updating the denormalized column family structures. The first one out here is more for, I think, for people who went from React to Cassandra, because the notion of a key value is always that you want to have coarse-grained objects. So given a product ID, get me all the attributes about the product. Yes, you can do that with Cassandra, but that's not how you want to be modeling it in Cassandra, because you want to be able to, again, go back to how you want to query the data set. And I think I covered the other aspect where if you have 2 billion columns in a row, you just want to update the column in question, not necessarily do a read and a write. The reason for putting up this slide is I know there is a lot of geek terms out here. So for people who want to keep clicking on pictures, you're welcome to do so. But essentially the theme is every new platform that you actually end up implementing, the basic principles, the guiding principles, and how you actually scale that platform fall upon how you actually measure the performance of this platform. So in other words, you actually have to model. There is no substitute for workload modeling. You will have to actually model in terms of your read-write access patterns, in terms of knowing all the access patterns that drive towards a load. And then you have a variety of, I mean, some of these terms that are out here are not necessarily Cassandra specific. You have to monitor memory use. You have to monitor CPU use. You have to monitor whether the data gets replicated from one data center to another. And let me tell you this, if you have to replicate data from one data center to another, you will be going through, pick your number, as many firewall contexts as you can think of. And you need to be able to have firewall connections that will not get tripped up, because you will forever be in this repair state if idle connections get tripped up. So those were some of the challenges that we actually had, because when we had to actually have data replicated from one data center to another, I mean, we were going through 6, 7, 8 firewall zones, and each would have its own policy in place. And we had to actually weave a way where we could establish a connection and essentially use the gossip protocol to find out that these connections are always live. So there were a lot of tunables at the OS level that we had to be doing. And again, the proof is in the pudding in terms of how it actually scaled. With that, I'll turn it over to Joel. He'll probably walk you through how we actually started the introduction of these NoSQL platforms at Best Buy. And we'll take up questions after that.
OK, I'll try and be quick, because I know I'm stopping you all from getting to happy hour at this point. The way, NoSQL systems are new, or not new, but in the last 3 or 4 years, they're pretty new. And it's not like you're going to go find somebody with 5 or 10 years of NoSQL experience. So when we built these teams, what we did was we started each of them with a project. And we took very good developers that we either know that had worked on other projects for us, or that we went out and just found in the marketplace. And none of them had any NoSQL experience, because really it just hardly existed in the Twin Cities at the time. So, but what worked out very well for us is to basically give the technology to a project team and allow them to start to use the technology to do the things that we wanted to do with it and allow them to learn a bit and write a lot of code and then scale up and figure out where all the issues were. But then as you get on to a year or two out, the product team no longer wants to spend all of its time working on the technology part of this, the Riak or the Cassandra implicitly, but to start to have a team take over that as infrastructure. So what we have done is we've taken Riak and we've brought it down to an infrastructure team to allow it to be used across at least bestbuy.com at this point. So now we have multiple teams using Riak and a single team managing the infrastructure. But it worked very well for us to start it with a project team so that we could actually learn how these systems work. I think that was the whole slide. So next step. And then at the end, like I said at the beginning, this wasn't going to be a, which is better, because what we've actually found is that they both work very well, and they both have their unique use case. I think some of you, if you're keeping track and keeping score, some of the things that are very different between Riak and Cassandra is the hub and spoke model that we use in Riak works very well with Riak, and Cassandra is built as a single ring that spans the whole multiple distribution set, is distributed across multiple data centers. And both of them have been extremely reliable for us. So as I said, Riak has been in production for 3 years. We've had multiple minor failures, but the ring itself has never failed in that entire time. And Cassandra went through our first holiday this year as taking all the logins. So if you logged into bestbuy.com since about October of last year, you've been actually hitting this Cassandra system we've just been talking about. And if you really want to test it out and you have accounts on Cinema Now or My Best Buy, you can go log in through those systems too. You're actually hitting this system to log in. So we have a single login across all those properties. There's a bunch of differences. Replication patterns are different. Read and write treatment is different. Our Riak is very read-oriented. The Cassandra system is very write-oriented. And the deployment of these things are very different. But in the end, both are highly available, both are very resilient, and both work very well across distributed systems. So hopefully, if you got nothing else out of this, you can be considering both these systems. They both work extremely well in the way that we've been using them. So with that, you can ask questions. We can go look at if anyone has actually typed any questions into the voice hive thing. We can remind people that's where you go if you want to type in a question, or you can just raise your hand, or you can just go out to the happy hour. So let's take questions in the room first.
So I saw that for Cassandra you got one ring, but for Riak you had two separate rings. Is there a reason there wasn't one ring that crossed data centers with Riak?
So the Riak, the architecture is the hub and spoke model. So there's one ring in the data center, and there's a ring in every cloud. So it actually is multiple rings. And so the reason for that is because when we lose the connections between the data center or the clouds, that ring just keeps on operating as if nothing happened. So those guys are going for the happy hour. Way in the back.
Which one was easier to set up, maintain, and to...
Wait, those are good questions. I'm going to say that they're both, at the level that we use them at, they're both hard. You have to spend a lot of time tuning both of them. For us, what we found on the Riak side, on the first holiday that we used it on, the replication between the data center and the cloud actually wasn't working that well. We actually called Basho. They came in. We had people on site for about 2 weeks, where we spent that entire 2 weeks trying to make this replication go faster. And so it was a pretty extended effort to get from where we were at to the replication that we needed for the holiday period. And that occurred over a course of about 2 or 3 months. So it was a lot of effort to get to that point. I don't know if you had similar issues with Cassandra?
Again, you will have to end up measuring your data replication aspects tied up with your system metrics. I don't think there is a silver bullet with either of these solutions.
So currently with your data model, you have a traditional data warehouse with Riak that feeds Riak. Is that whatever, it's a SQL data?
We have a classic DB relational database.
And I'm guessing your goal is eventually to get rid of that classic, and that's why you didn't go with something like Elasticsearch product you built.
Yeah, so when we've been building out these systems, we've been trying to stay away from vendor-specific technologies and clouds. So Elasticsearch in particular would have been tied us to Amazon. So okay, so sorry. Solar Lucene, we actually use Solar Lucene for our search already. But in terms of the classic database, is never going to go away. We'll probably always have it at some place in our system. They work very well for certain things that we want to do.
I'll add one more. I mean, if your question is more tailored towards have we adopted a Lucene or a Solar model over a NoSQL platform, we are working on a model where we are really looking at if there are use cases that are not currently supported, and we may possibly end up having to do a Solar or a Lucene. Lucene probably not, a Solar over a Cassandra maybe. But at this point, again, it goes back to your data structure, because whether it's a Lucandra or a Solandra, you're actually ending up using the column family structure. And so if you model your column family structure appropriately, I don't think you actually can do a lot of use cases around search without the use of a Solar.
How many products are you indexing?
It's about 650,000. So questions? Or we'll try these. Do we have a Chaos Monkey? No. We often talk about it though, and it's definitely something that we've talked about implementing. Mongo, that's a whole separate topic if we want to get into that. People can rewind their heads 3 years, Mongo at the time was pretty new and had a lot of scaling issues. So back when we were picking these systems, it wasn't high on the list in the things that we thought could actually scale to BestBuy.com's needs. Nowadays, it's probably, it's probably perfectly fine for these type of uses. How easily can nodes be added to support bursts? Do you want to go on that one with Cassandra?
I mean, when we talk about adding data nodes, yes, you can easily add data nodes, and the token distribution and the replica distribution, that's the simple part of it. But then when you have to actually look at how does your application or your API infrastructure actually use the data nodes behind the scenes, you actually cannot necessarily do an auto-scaling infrastructure for those reasons, where you end up having to have a library that you will have to use that gets configured via other processes that are in place. So you can actually add data nodes, you can bring down nodes, you can add nodes. There's actually nothing that is going to result in a customer impact or an experience impact. But then when you actually end up having to leverage those nodes with your API infrastructure integrated, that's really where the challenging aspects come in.
We actually try and build the systems out to the size we think we're going to need for prior to scaling events, because they do take a little bit of time to take all the data onto the servers. So it's not something you can spin up in 5 minutes, like in a cloud like you normally can. You can spin up the system in 5 minutes, but then you got to start taking data into it before it's useful, and that takes a fair amount of time on the Riak side. Another why Mongo or Couch. Again, we weren't going for JSON-style databases when we were making these. We were going for key-value pair and sparse columns. So in terms of our usage, they didn't seem to be good fits. Not that both of them are actually very good NoSQL systems. How much data do you have in each system? Actually, I don't know that one.
I'm assuming you're talking about, we are close to terabytes or petabytes, if you will, depending on which data set you're looking at. I don't think we can just arbitrarily say these are the number of customers or these are the number of products that are there in our ecosystem, but just let's put it out there that there are many millions of products and many millions of customer data.
Do we have data stacks? Can I answer that question? The last one? Is that okay?
It's okay to answer. I think we've published that on another spot.
Okay, yes, we use data stacks. Great. Any other questions from the room?
Just to be, Joel, we use both open source though and data stacks. Right?
Okay.
So we have the open source just native in a lot of apps as well. It's
So-
not all Cassandra instances or data stacks?
So we use DataStax, but we also use the open source version.
Is that a question? And for Cassandra, how are you guys backing it up besides the replication?
Essentially, we take care of ensuring that the replication factor is appropriately set. So you at least have more than one copy of a given row in more than one replica set. And typically, we just rely on snapshots and essentially look at restoring the data from a snapshot. And we kind of keep the snapshots going on a periodic interval.
I actually have a picture of the servers, the Cassandra rack, but I'd have to go find it. I'm assuming what you mean is they are big servers. Very large, pretty much large as you can get, because they obviously take a lot of processing and RAM. They use a lot of both.
I think there was a question.
How many nodes are in your Cassandra array?
Within a data center, you're probably talking close to a dozen for this specific use case. There are other use cases where we kind of have several or close to 100 nodes. So it again goes back to whether you're capturing clickstream data or real user preferences.
So you have more than one cluster you operate?
Yeah, so we have, think of it as 2 to 4 data centers. If you were to account for the edge providers as also being one of your data centers.
Let's see. Do you contribute financially to open source projects? I don't know if I can answer that one either. We have contributed back to open source projects in terms of patches and whatnot that we've made over the many different types of open source that we have used in the past. So, but the financial one, I guess I don't know.
What version of Cassandra do you use?
We started at 0.7, and we are probably close to Cassandra 1.x. I'll just leave it at that. We are yet to migrate over to SQL 3, so we currently still use ST and Accent or Hector to connect.
Great. Well, thank you, everyone, for coming. Thank you for sharing Best Buy with us.